Why do sine, cosine, and tangent appear in right-angled triangles, even though that's not where they truly originate? In this video, we'll go beyond the triangle and understand what these ratios actually represent in real motion through space, where direction and projection become the real foundation. Let's start with a simple motion in space. Imagine we have a car, represented by this orange dot. Now here's a question. If this car starts moving, can we tell exactly which direction it is moving in? Actually, no. That would be impossible unless we already have some reference directions. So first, let's create them. Now we have the four primary directions: north, south, east, and west. And once we have these reference directions, understanding motion becomes much easier. All right. Now let's move the car. The car travels from point A to point B. And clearly, we can see that the car is moving somewhere between the north and east directions. But now another important question appears. While moving from A to B, how much distance did the car actually cover toward the north? And how much toward the east? To understand that, first let's draw a reference direction line representing the north-south direction. Now, let's project the total distance AB onto this direction. And remember this carefully. Whenever we project motion onto a direction, we always project at 90 degrees. Now look closely. Even though the car is moving diagonally along AB, the projection shows how much distance is being covered only in the north direction. Similarly, let's create the east-to-west reference direction and project the motion again. Now we can see how much distance the car covers specifically toward the east. So what does this actually mean? It means any motion can be divided into components along any direction we choose. In this example, we only use two directions. But in reality, we could measure the car's motion along any reference direction we want. Clear? Good. Now let's move beyond the primary directions and observe motion using different reference directions. This is the real power of projections. They allow us to break a single motion into multiple directional motions. Now let's see what happens while the car is actually moving. Watch carefully. As the car moves from A to B, it is simultaneously covering distance in two different directions. Now suppose the total distance AB is 3 meters. And the line AB makes an angle of 30 degrees with the horizontal direction. If an object moves 3 meters at an angle of 30 degrees, then experimentally, we observe something interesting. The object covers 1.5 meters vertically and 2.598 meters horizontally. Now you might ask, how do we already know these values? Simple. These values come from real measurements and mathematical analysis of motion. So don't worry yet about where the numbers came from. Right now, focus on what they mean physically. We already know the vertical and horizontal distances corresponding to 3 meters of motion. But what about just 1 meter? How much vertical distance would 1 meter of motion produce? And how much horizontal distance? Now things become interesting. Because this is exactly where mathematics enters. Mathematically, we use division. If 3 meters of motion produces 1.5 meters of vertical distance, then dividing gives us the vertical distance produced by just 1 meter of motion. And similarly, dividing the horizontal distance by the total motion gives us the horizontal distance produced per meter of motion. After calculating, we find that, for every 1 meter along AB, the motion produces 0.5 meters vertically and 0.866 meters horizontally. Now keep these numbers in mind, because they are about to create something very important. A right-angled triangle. Look carefully. The vertical distance becomes the height of the triangle. the horizontal distance becomes the base. And the original motion AB becomes the hypotenuse. But there's a very important detail here. The horizontal and vertical directions themselves are already perpendicular to each other. That means the projected distances along those directions must also form a 90-degree angle. And that is exactly why a right-angled triangle appears naturally. Nothing mysterious is happening. This triangle is simply the geometric result of projecting motion onto perpendicular directions. So the conclusion is, the height of a right triangle is actually the projection of the inclined line onto one direction. And the base is the projection onto another perpendicular direction. And the exact values of height and base depend entirely on the inclination angle of the line. In other words, the angle the motion makes with the base direction. Now let's move forward. We know that line AB makes a 30-degree angle with the horizontal. And in a right triangle, the moment we choose an angle, the definitions of perpendicular and base become dependent on that angle. The hypotenuse stays the same. Now let's understand sine. For angle 30 degrees, the perpendicular side is BC and the hypotenuse is AB. So, sine 30 degrees equals BC divided by AB. But what does this ratio physically mean? Think carefully. When we divide BC by AB, we are finding how much vertical distance is produced per meter of motion along AB. And we already calculated this earlier. So physically, sine represents vertical distance covered per meter of hypotenuse. Now let's understand cosine. For 30 degrees, the base is AC and the hypotenuse is AB. So, cosine 30 degrees equals AC divided by AB. This tells us how much horizontal distance is produced per meter of motion along AB. So physically, cosine represents horizontal distance covered per meter of hypotenuse. Now let's look at tangent. Tangent 30 degrees equals BC divided by AC. But this time, something is different. In sine and cosine, we compared the projected distances with the actual motion AB. But in tangent, the hypotenuse completely disappears. Now we are directly comparing the two projections themselves. Let's understand what that means physically. As the car moves along AB, it simultaneously covers some horizontal distance and some vertical distance. Now imagine this carefully. Suppose during the motion, the car has already covered exactly 1 meter horizontally. At that exact moment, how much vertical distance has also been covered? That relationship is what tangent measures. So tangent is not comparing motion with the hypotenuse anymore. It is comparing vertical change with horizontal change. In simple words, for every 1 meter moved horizontally, how much vertical distance is gained? Now let's examine the other angle of the same triangle. The angle at point B, which is 60 degrees. Now something interesting happens. When we use sine, cosine, and tangent with 60 degrees instead of 30 degrees, the perpendicular and base sides switch roles. But why? Because perpendicular and base are not fixed sides. They depend entirely on the angle we choose. Earlier, for 30 degrees, BC was opposite. But for 60 degrees, AC becomes the opposite side. And since sine always relates opposite side to hypotenuse, the meaning changes automatically. Now watch the animation carefully. As the motion goes from B to A, there is simultaneously motion from C to A and from B to C. One becomes vertical with respect to the chosen angle and the other becomes horizontal. So the final conclusion is this. In the same right triangle, changing the reference angle changes the definitions of perpendicular and base. The triangle itself does not change. Only our perspective changes. And that's how perspective shapes trigonometric ratios. We'll leave the motion here, for now. See you next time.